Hello everyone, my name is B. Jagadish. My data structures techtalk topic is theory and applications of B-bit minwise hashing. I am from my roll number is 21951800463. I am from ECA section. Let's get started. First, let us see what is minwise hashing. Efficient approximate computation of set similarity in very large data sets is a common task with many applications in information retrieval and data management. One common approach for this task is minwise hashing. So with this minwise hashing, any complicated task can be done easily through this minwise hashing. To address this issue, Broder and his colleagues developed minwise hashing formula in their seminal work. Suppose a random permutation pi is performed on omega, that is pi east omega to omega equal to 0, 1, d and so on. An elementary probability argument show that probability minimum pi S1 intersection S2 by S1 union S2 equal to R. After k minwise independent permutation pi 1, pi 2, so on pi k, one can estimate R without bias as a binomial property. Rm equal to 1 by k sigma. It is a formula that is Rm equal to 1 by k sigma k j equal to 1 to k 1 bracket start minimum pi j s1 equal to minimum of pi j s2 2. We will frequently use the terms sample and sample size for minwise hashing. So these are two terms which we use in the minwise hashing. A sample is a hashed value minimum pi j si which may require 64 bits. Since the original minwise hashing worked 2, 4, there have been considerable theoretical and methodological developments 3, 5, 13, 15, 17, 18, 22. Applications. As a general technique for estimating set similarity, minwise hashing has been applied to a wide range of applications. Many of the applications of minwise hashing are targeted at detecting duplicates or pairs of somewhat high similarity. By proposing an estimator that is particularly accurate for these scenarios, we can reduce the required storage and computational overhead dramatically. Here, the computational savings are a function of how the minwise hashes are used. For any technique that does compute the pairwise similarity for a large subset of all pairs, the computation is typically bound by the speed at which the samples can be brought into memory. As the computation itself is simple, hence the space reduction of our technique offers directly translate into order of magnitude speed up as well. However, even with the data size reduction, computing all pairwise similarities is prohibitively expensive in many scenarios. This has led to a number of approaches that avoid this computation by grouping subsets of the samples into buckets and only computing the pairwise similarities for items within the same buckets. This approach avoids the quadratic number of comparisons at the cost of some loss in accuracy. Examples of such approaches are super singles or techniques based on locally sensitive hashing (LSH short form). B-bit meanwhile hashing. Let us see what is B-bit meanwhile hashing. In our scheme, a sample consists of B bits only as opposed to e.g. B equal to 64 bits in original meanwhile hashing. Initially, using fewer bits per sample will increase the estimation variance at the same sample size k. Thus, we will have to increase k to maintain the same accuracy. Interestingly, our theoretical results will demonstrate that when resemblance is not too small, which is the case in many applications. Example, consider r greater than equal to 0.5, the threshold used in 2, 4. We do not have to increase k much. So, already it is decreased value. So, we do not have to need increase k much at all. This means our proposed b-bit meanwhile hashing can be used to improve estimation accuracy and significantly reduce storage requirements at the same time. For example, when b equal to 1, r equal to 0.5, the estimation variance will increase at most by the factor of 3. In order not to lose accuracy, we have to increase the sample size by a factor of 3. If we originally stored each hashed value using 64 bits, the improvement by using b equal to 1 will be 64 by 3 equal to 21.3. Algorithm 1 illustrates the procedure of the b-bit meanwhile hashing based on the theoretical results in section 2. Algorithm 1. The b-bit meanwhile hashing algorithm applied to estimating pairwise resemblance in a connection b-bit applied to estimating pairwise resemblance in a collection of n sets. Input sets Sn subset n 0 1 d minus 1 n equal to 1 to n. Pre-processing generate k random permutation pi j omega j equal to 1 to k for each set Sn and each permutation pi j. Store the lowest bits of min pi j Sn denoted by en I pi j I equal to 1 to b. Estimation. Use two sets S1 and S2 as an example. Compute PB equal to 1, PKJ equal to 1, NQB I equal to 1. 1 E1 comma I pi j equal to E2 I pi j. Estimate the resemblance by RB PB minus C1B 1 C2B where C1B and C2 are theorem 1 in section 2. Locality sensitive hashing is a set of techniques for performing approximate search in high dimensions. In the context of estimating set intersections, there exist for estimating the resemblance, the accuracy and the Hamming distance. Our b-bit meanwhile hashing proposes a new construction of LSH family. A related approach is a conditional random sampling, which uses only a single permutation and instead of single minimum retains as a set of smallest hashed values. So it is a related approach is a conditional random sampling which uses only a single permutation and instead of single minimum returns a set of smallest hashed values. Thank you.